Um, and we are looking at question number 25. Um, here is the setup. I put a point A, which is where you're trying to find the point where that is dropped from. First thing to look at is to say that the energy is conserved. The total at A is the total at B is the total at C. And what types of energies could it have at A? It could have gravitational. It could have kinetic. Well, it couldn't have kinetic because the velocity is zero, and it couldn't have uh, elastic because the spring hasn't been stretched at all. What kinds could it have at B? It could have, depending on where you made your height zero, it could have gravitational, could have kinetic because it is moving, and it could not have elastic because it hasn't compressed the spring yet. It is just about to touch the spring there. And then at C, depending on where you put your height zero, it could have gravitational, couldn't have kinetic because it's not moving, and it definitely is compressing the spring now. So these are the types of energies it possibly could have based on where you make your height zero. Now, I like to simplify the problem and say that height zero is at the lowest point that the object goes. Not the table, because that would mean that that C would have gravitational, but the lowest point that the ball goes in this. So I make my height zero at point C. So if that's the case, redraw this. Height zero is here. B is 16.16 meters up. A, I don't know how high it is. That's what I'm looking for. And so this is what my height, my velocity, my compression, my x value would be for the different points. Now if I look at this, I don't know the mass. That's not fun, but if I pick the right ones of these, I can maybe get around that. So let me pick point A and point B and say, all right, if I know the total at A is equal to the total at B, A only has gravitational potential, B has gravitational potential, and kinetic energy. All three of these have mass in their terms. And mathematically, that means you can divide by mass on all the sides, on both sides, and it goes away. Putting in the numbers that I know, I found out that it's 0.6 meters above my height zero, point C, and I'm not sure I got this calculation right, but about 1.1 meters above the table. That's what I got. And then for part B, what's the spring constant? I'll say the total at A is the total at C. So the total at A is the mass, which I'm now given as 0.3. It's 0.96 meters up in the height if I'm making this so that it's height zero. And we get the spring is compressed, 0.16 meters. So I get a spring constant of about 225 newtons per meter. All right, again, you got around not knowing the mass because each of the terms, if you pick the right points to look at, each of the terms have mass in it, which means mathematically you can divide it out. And you would get the same answer no matter what mass you put in here, because if I put 1, that's a 1 and that's a 1, or 2 and that's a 2 and that's a 2, or 4 and that's a 4 and that's a 4, all those would eventually wash out mathematically.